Yay.
Okay, so, but hopefully, some of you are watching them. Hopefully they're useful. The production quality is low, I know, so, but there it is. It's better than last semester when there were no videos. All right, so where were we? We were talking about acids and bases, and what we'd said about acids and bases was that we have a new definition, and that new definition is the Bronsted-Lowry definition of an acid. So acids are proton donors, Bronsted-Lowry bases are proton acceptors. Here's number 4, we'll pick up here. And what we're doing is we're assigning acids and bases to everything now in acid-base reactions, because Bronsted-Lowry theory is a more expansive theory of acids and bases, although every acid and base that we thought we knew before still qualifies. HCl, still a strong acid. Acetic acid, still a weak acid. And we'll just find new things. And one of them is water. Water is what's called amphoteric. Amphoteric means it can function as either an acid or a base. Can function as either an acid or a base, depending upon what other species are in solution. Depending upon or on what other species are in solution. And we've already seen this a bit. So when ammonia was put into aqueous solution, we said ammonia was a base and water was an acid. When HCl was in solution, and these are on the previous pages of this chapter, HCl was the acid and water was the base. Now, we're going to auto-ionize water. That means we're going to treat water as both an acid and a base. And these are purely definitional. So water in water, some of the water molecules will give a proton to other ones. Those will create hydronium and hydroxide ions. And so by definition, since this water donated a proton, it is the acid. The other one received a proton, it is a base. On the other side, we do this in both directions. We are not surprised to find that hydronium is again an acid. And we are not surprised to find that hydroxide is a base. In fact, hydronium is always an acid. Hydroxide always a base. And this has a K value. And it is the same K value we had last semester when we talked about this reaction, H2O going to H plus and hydroxide minus. We said last semester this was called Kw, and the value was 1.0 times 10 to the minus 14. The only thing we've done now is we've added a water molecule to both sides. This reaction here is equivalent. Kw equals 1.0 times 10 to the minus 14. And what you can imagine is, if you add the potential energy of a water molecule to both the reactants and the products, the potential energy of each side is still balanced. It's a longer stretch before we talk about how that works in terms of equilibrium constants, but the short answer is it does. Questions? We will use these equations when we talk about pH. We will use these equations quite a bit. But they're equilibrium constants. We can write the equilibrium constant, and I'll do it for this reaction on top here. Kw is just a named version of Kc. Kw is the water ionization constant, or the water equilibrium constant. Do liquids show up in equilibrium constant expressions? No. And in fact, with hydronium instead of hydrogen, replacing it, this is the same expression we had last time. Should look familiar. And what we're seeing is, in addition to Kc's and Kp's, now we have a Kw, follows all the same rules as Kc and Kp do. Products over reactants, coefficients which are 1 are still exponents. Other amphoteric species, bicarbonate ion, has an H in the front. We will treat this as an acid. Leaving us with hydronium and carbonate ion. We will make all of our assignments based on what's donating and what's receiving or accepting the proton. For those of you who remember back to Chemistry 400 in the antacids lab when we had calcium carbonate in the top care / Tums, finally, carbonate ion is a base. No wonder it neutralized the HCl. We'll talk more about this as we get there, but now it's a base. We can also treat HCO3 minus bicarbonate. As a base. Move the proton, the H plus, in the other direction. And what's the formula of the other species right here? H2CO3, also known as carbonic acid. And we label everything up. We have an acid and a base on the reactant side, an acid on the base on the product side. And this is still relatively new, but that is how it will be. Question, Dylan?
Do both these reactions happen at the same time if I mix both bicarbonate and water?
Do both of these reactions happen at the same time if I mix bicarbonate and water? The short answer is no. The next longest answer is, well, we haven't talked about them yet, but these reactions will have equilibrium constants. And the larger the equilibrium constant, the more of each of these reactions will happen. And we will see that one of them is much more likely to occur than the other. But that's where we're going. Yeah. Any other questions? If not, then let's go over to slide number 5. Conjugate pairs are very important in Chemistry 401. True. Now we'll talk about them. And what is the conjugate base for CH3COOH? Well, first thing, let's check in here for a second. So, Acetic acid, strong acid or weak acid? It's a weak acid. And we're going to talk enough about weak acids that we will come up with capital W, capital A as our abbreviation for weak acid. And the conjugate base will have one less proton, that's one less H plus, than the conjugate, and then the weak acid. Okay. And yeah, so take away an H plus from CH3COOH, acetic acid. Which H plus will we take away? The one way over here. We will be left with the acetate ion. And one of the things I will point out to you is that as we go through weak acids and their conjugate weak bases, or conjugate bases, you're going to see ions that you've already memorized from Chem 400 greater than 90% of the time. So expect that. Questions about this? If not, well, let's do this example. What is the conjugate acid? And this is where things get a little weird. But the reason we're going to solve this problem, and we'll write weird. The reason we're going to solve this problem is because anything has a conjugate weak acid. Anything has a conjugate weak base. 90+% of the time in the problems that you solve, there'll be things that you've seen before, but the rules are completely general. And when you get to organic chemistry, all bets are off. Right? You'll talk a lot about acids and bases. And you'll be interested, well, maybe not in this example, but in going in the non-regular examples, let's say. But, so what is the conjugate acid? Conjugate acid, for whatever it is, always has one more H plus. And granted, we don't know where to put it, right? That's fine. And it doesn't matter, but it looks like this. And it has a plus because we added an H plus. That sign is important. And this is a species you will see in organic chemistry. Okay. All right. So, and now, oftentimes what we will see is we'll write them like this. Because this is a conjugate pair. The slash in the middle is not a division symbol. It's just meant to tell you they're together. This is a conjugate pair. Marissa? Good question. Do only weak acids have conjugate bases? No. All acids and bases have conjugates. And we will be interested in all of them. And we will talk about all of them as well. However, weak acids and their conjugate bases will be the subject of buffers. And that's an important topic too, although we'll be interested in all. Write the conjugate pair down here as well. Typically, you write the acid on the left. You don't have to, but that is typically how you do it. Okay. Question, Marissa?
Okay, so is this rule true for all species or just for weak acids? The one, like one less and one more?
Oh, the one less and one more is true for all species. Yeah, no, we will do it. And just for fun, let's talk about HCl. It's a strong acid, right? What's its conjugate base?
Cl minus.
Cl minus. Exactly. In fact, what we can do now is, and I apologize for this, but we're going to do it. Let's go back to this one and find conjugate pairs. Okay, and we'll start down here. Are carbonic acid and bicarbonate ion only different by an H+? Yes, they are a conjugate pair. What about H2O and hydroxide ion? Also a conjugate pair. What about bicarbonate and carbonate? Also a conjugate pair. Hydronium and water? Also a conjugate pair. I'm starting to notice a trend. And it makes sense because these are just proton transfers, so of course you're going to end up with the other conjugate. That will always happen. And we could go back here and we can't tell which water is which, but since we call this one acid, we would say this is its conjugate base. Acid, conjugate base. This will always be true. And we'll do more of it, but we'll just label that one for now and we'll save more of it for the next one. Now let's talk about acid strength and Ka. Remember from last time, Ka is for a specific reaction. So let me write out the Ka reaction. It is whatever the acid is plus water. We see that in this particular case, since we have a weak acid, water will be the base. That's what I meant by water, whether it's acid or base, depends on what's around it. We get hydronium plus acetate ion. It says all acids have a Ka reaction and a Ka value. I'm going to write the Ka value over here. Ka values are tabulated on your conversion and equation sheet for all of the acids, so you don't have to know them. You will have to know how to interpret them now, and we'll talk about it. If you look it up, the Ka for acetic acid is 1.8 times 10 to the minus 5. Is that a large or small equilibrium constant value? Small. That means this reaction favors reactants. That's in line with what we learned in Chem 400, which is this reaction goes less than 5%. That's the old way of saying it. Now we have numbers. We're starting to have numbers to back it up. Conjugate pairs. We have a weak acid. We have its conjugate base. We're not going to prove this yet, but I am going to state it so that you have this for your notes. It turns out that weak acids always have their conjugates be weak bases. So this is a weak base. Weak acids always have conjugate weak bases. Question?
Does it work the same way for strong acids? Always have strong conjugate bases?
Hold on.
All right.
We're so close. But we do want to explore that trend. And you'll oftentimes see weak acid, conjugate weak base, because especially when we talk about buffers, you'll always have them right next to each other. We have another set of conjugate pairs. We have an acid that shall remain unclassified for now, but we will talk about it. And the base. Let's do HCl next. All right, but they are a conjugate pair. That's what I want to say. All right, now let's do the strong acid. Same kind of thing, it's a Ka. Ka reactions always look like this. Acid plus water goes to hydronium plus conjugate base. We said that conjugate base for HCl on the previous slide, or on the previous slide was Cl minus. So this is a conjugate pair. This is a strong acid. And it has a Ka value too. Ka equals 1.3 times 10 to the plus 6. And I say plus, you don't have to write it, because almost all of the acids we find will be weak acids, and they will have negative exponents here. This is a positive exponent. Where is the position of equilibrium with this reaction? Towards products, right? Well towards products. That is in line with this reaction going 100% in Chem 400 and 99.99999% or so, now that we know about equilibrium. Effectively 100%. All right. The stronger an acid is, the weaker its conjugate base is. So I'll leave a little space here to do the connecting thing, but so stronger acids have weaker conjugate bases. There is an inverse relationship there, meaning the better that this is at giving up a proton is the worse this is at taking one, since they're related to each other. Now, okay. But I've already said that weak acids go with weak bases. So now, strong acids, their conjugates are, I call them inert bases. You might recognize chloride from last semester almost always as a spectator ion. It does nothing. So we saw it being mostly inert last semester as well. Inert means non-reactive. An inert base specifically means non-reactive towards being a base. Does not affect pH. Does not affect pH. And that's a lot of what we're doing with this talk about acids and bases, is figuring out what are the pHs of these solutions and how do we change them. So now we can connect them. It is a conjugate pair. And weak goes with weak. Weak acids have weak conjugate bases. Strong goes with inert. Also true of strong bases. Strong bases have inert conjugate acids. Everything has a conjugate. And, no, we still haven't done these. They're still conjugate pairs. Whoa. We can write a Ka for this. I bet you could. Whatever it is, I told you it's an acid. Add water to it, transfer a proton. What the? What's the other product? Water. Anybody care to take a guess at what the Ka value is for this one? Just one. Because the form of it is hydronium over hydronium, whatever it is, it's the same. K equals 1. And hydronium is the strongest acid that can exist in water. And its Ka value is 1. What that means is anything that has a Ka value larger than that will be converted into hydronium. There's no more HCl anymore. You have hydronium. And this one has a smaller Ka value. What percentage did we say this stayed in solution? Greater than 95%. This is not stronger than hydronium, so this can exist in water. Okay? Anyway, so again, this is actually related to some of the things you will eventually do in organic chemistry next semester. You'll be interested in what kind of acids can exist in water versus other things. And we'll have a lot more to say about it. You can now write a Ka expression for anything. And you can look up a lot of them for the common acids on your conversion equation sheet. Okay. Oh, we're not done here yet. Now let's talk for a few minutes about pKa. You remember what pH was? What was the equation for pH? pH equals negative log of the hydronium ion concentration. It was the power, the exponent of hydrogen. pKa is the minus log of Ka. So that little lowercase p, wherever you see it, it means take the minus log of whatever it is you're doing there. We'll write some pKa values down here. pKa of acetic acid, 4.74. It's easy enough. I know you can do it on your calculator. pKa here, minus 6.11. pKa here, well, log of 1 is 0. And we want to establish two trends here. One is, as Ka gets smaller, the acid gets weaker. As Ka gets smaller, from 10 to the minus 5 to 1 to 10 to the plus 6, the acid gets weaker. And as pKa gets larger, the acid gets weaker. Oh, yes. Those are two trends. when I box something, even, oh, okay, there's not a box there, but as I put things in some sort of weird shape, that means they are important to remember. Please remember both of those trends. Although they're also similar to the trends in pH. pH, as the concentration of hydronium got bigger, the pH got smaller, and you can see the pKa's and NKa's had run opposite trends. All right, that is all I think we had to say about that. Questions? Yes, Anna Marie. There are no units with pK. I know. This is the part where I get sad. There are some Ka values. That exact copy is on your conversion equation sheets. Now back to ice tables. We could not do this problem last semester. We said we do not figure out the pHs of weak acid solutions. Now we are finally ready. What is the pH of a 0.100 molar solution of acetic acid? Acetic acid, well, a little blurry. There it is. 1.8 times 10 to the minus fifth. We will need an ice table to do this problem. The ice table will involve the Ka reaction for acetic acid. Our reactants are acetic acid and water. Our products are hydronium and acetate. And our Ka value is 1.8 times 10 to the minus 5. This is a molarity ice table, as has everyone been either molarity or atmosphere so far. We start with an initial concentration of 0.100 molar. We start with, we don't care about water because it does not appear in our equilibrium constant expression. We have squiggly equals sign equals 0 for hydronium because this is in water. If you have absolutely pure water, nothing else, pure as the undriven snow, what is the pH? 7. And if the pH is 7, what is the concentration of hydronium? 1.0 times 10 to the minus 7. That's why there's an approximately equals 0 there. This time we'll put an asterisk. The concentration of hydronium in pure water is 1.0 times 10 to the minus 7th molar. This is insignificant for solving this problem, because we'll see that that's close enough to 0 that we will make the approximation that it is 0. But I always write approximately equal to 0 there, so that at some point in the back of my head, if I get down to an equilibrium concentration that is also 10 to the minus 7, I will then say, wait a minute. Something funny's going on. And by funny, I mean weird. All right. Anyway, and for now, what I'll tell you is, I'll tell you, or yeah, I don't know. Let's see if we see anywhere it doesn't matter. There are zeros on the right. That means that the QC, the reaction quotient the same expression as the equilibrium constant, except not at equilibrium. We'll have 0 times 0 over 0.1. It will equal 0. That means the reaction must go to the right to get to equilibrium, which is always true when there's a 0. And since the reaction must go to the right, the plus x's go on the right-hand side. We must be making product. Lovely, all one coefficients. So when we fill in, we only have powers of 1 in our concentrations. We have we take our equilibrium values, place them into our Ka expression. And set it equal to our Ka value. Questions about that setup? This is pretty much the setup every single time for Kas. We're going to be doing this like 10 or 20 more times in the next few chapters. Looking at my Ka value, I see it's 10 to the minus fifth. I want to assume that this x is much smaller than 0.1. I will do that. We'll assume it equals 0. That's the assumption. We have to check whether it's, when we solve for x, whether it's less than 5% of this 0.1. That's what we're left with. X squared over 0.1 equals 1.8 times 10 to the minus fifth. Easy enough to solve. X equals 1.34 times 10 to the minus third. And X is our concentration of hydronium. And concentrations do have units, so I slid a little m in there for molarity. Okay. Skip the algebra, but it's pretty straightforward. The only thing we're asked, though, is for the pH. pH is just the same as last semester. If you have the concentration, well, we called it H plus last time, but now pH. Now pH is the negative logarithm of the concentration of hydronium. Just like last semester, this 3 here means that our pH will be either be the same number or 1 less. We're not surprised when this is 2.87. Done. Any questions?
Can you explain why, again, I'm still kind of stuck on why you assume that your x is 0 on the denominator?
Good question. The question is, why did I assume this x equals 0? I did that to make the math easier. And I did that based on the fact that since Ka is small, that means that the position of equilibrium lies far towards reactants, which means that the amount of reaction will be small. That's an assumption. We double check it. If you double check it, you'll see this is 1.3% of that number. And as long as it's less than 5%, it's a valid assumption. I think there was a question in the back, and then maybe Marissa. Was there a question back here? No? Marissa, do you have a question?
Yeah, I just forgot how you checked it. But
Yeah. Okay. How do I check it? Basically you say, good question. Well, we have some space over here. So it's going to be X, which is also known as our amount or extent of reaction, how much reaction occurred, over concentration of our reactant initial and so you get 1.34% for this. 10 to the negative third. There's a negative up there. Yeah, sorry if you can't see it. Because it's the same answer. Yeah, this is a negative 3. Seems to be growing out of the center of the 3, I see. But it is a negative. Is that true? So if X is less than 5% of the initial concentration, is that true for all problems? Yes. If it is not true, if you get here and it is more than 5%, what do you have to do? The math. Do the math. Solve the quadratic equation. This one, yeah, no, there would have been a quadratic to solve there. It's not a perfect square. Any other questions? Mackenzie?
Can you repeat what you said to her about the small k value and how you assumed the x was equal to 0?
Yes. So this k, it's a ka, but it's really it's the same pattern as kc. And we said if any equilibrium constant was less than 1 times 10 to the minus 4th, that meant that it was very reactant favored. If it's very reactant favored, then as it makes products, it's only going to make a tiny amount. Our assumption is that it makes none, or really, our assumption is that whatever x is, it's insignificant compared to 0.1. And this is a very good point. I can ignore x because it's small compared to this number. I cannot ignore x that's multiplied by anything, right? I'm never ignoring these x's up here. I'm only ignoring an x that is subtracted or added from something much bigger. Does that answer your question, Mackenzie? That's an important point because, as I have mentioned repeatedly, you will solve 50 to 100 of these ice tables, and if you could do 50 to 100 less solvings of the quadratic, that would be nice. Another thing I'll tell you is, and I think I've said this before, but I didn't say it last semester, so I want to be clear about it. No programmable calculators on exams in this class, so I would suggest you do your homework with a non-programmable calculator and practice solving the quadratic, because you're going to have to. I don't know. I have not written the first exam yet, but I can almost guarantee you that at some point you will solve the quadratic on that exam. It's like I'm prescient. Maybe that's the word. I don't know. I can see into the future. It's my own future, so I don't know how much that counts. All right. Percent ionization. Percent ionization, well, looking at the example here, it's going to be the concentration of hydronium over the concentration of our acetic acid initially. It's actually the same thing I just did up here and erased it, but now we're putting it down here. It is formally called the percent ionization. Yeah, it's actually the same thing I just did, but I'll do it again. It is the percent ionization is 1.34%. Question, Marissa?
So is the formula just like concentration of hydronium divided by concentration of initial weak acid, or is it like whatever? It's always going to be hydronium, I mean.
So the question is, will it always be this formula with the acid? I would say this is actually a more general formula. However, we will almost always use it for the ionization of acids. And if you remember, we said in Chem 400 that weak acids were generally ionized less than 5%. Voila, we are now there to show it. Question, Aaron?
Is that like a little I down by the
Oh, yes, this is a little I, and I means initial concentration of our acetic acid. Any other questions? Different concentrations of weak acids have different pH values. What is the pH in percent ionization of a 0.500 molar solution of acetic acid? While I erase, would you make this ice table? It's the same ice table with a different concentration. Right. But now we're starting with 0.500 molar. We still don't care about the liquid. The hydronium still starts at approximately equal to 0. Acetate 0. Very similar to the last problem as far as the setup. And at the risk of making mistakes, I will now just jump to the fact that it is x squared over 0.500 minus x. And it still equals the Ka. We will still assume that we can ignore x. We will still solve it, and if we do, we get that the concentration of hydronium, which is x, is 3.00 times 10 to the minus 3 molarity. Skipping the math part. pH equals 2.52, and the percent ionization is 0.60% ionization. You could continue through and show that, the point being that higher concentrations have lower percent ionizations. And let me be more specific than that. Higher concentrations of weak acids have lower percent ionizations. Question, Marissa?
So you can determine the pH from the Ka value, or no, sorry, yeah, from the Ka value. Can we determine the Ka value from the?
Good question. So your question is, we can determine the pH from the Ka value. Can you determine the Ka value from the pH? Answer is yes. Remember in last lecture I said there were two types of ice tables. the one that was 90% of the time had X's in it, and we were solving for the equilibrium concentrations. The less than 10% kind would be you had numbers for the changes, and you could calculate the equilibrium concentrations, and then from that, K. If I give you the pH, you can know the equilibrium concentration of hydronium and work backwards to K. Good question. Good. So let's move on. What are we really doing when we calculate pH in a weak acid? There are two equilibria. Work with the largest Ka first. So what I mean by that is, example, when we have acetic acid and we know its Ka value, but it's aqueous. Aqueous means there's water around. Water is an acid. Water, well, we don't call water, we didn't do water's Ka value. But if we did, we can imagine saying water as the acid plus water goes to hydronium plus wait, we've done that before. Water plus water what is the K value for that? 1.0 times 10 to the minus 14. So we call it KW. It's really Ka for water, although you'll always call it KW in this class. And it's 10 to the minus 14. And you remember, those who had me, although I bet anybody who had Chem 400 got this information, you always have water, and the product of these two concentrations always equals this number. Do you remember that from Chem 400? We're ready to talk about that now too. Such a sense of closure today, perhaps. But this number, what we're doing really is we're taking the strongest acid, it's still weak, sorting out its ice table. Then when we do this pH thing down here, we're dealing with the next strongest acid, and that's always what you do. You always deal with the largest value of the equilibrium constant first. The next one, very rarely you'll have to deal with the third one to get the answer that you want. But the note, always deal with the largest equilibrium constant first, then the next largest, then the next largest, etc., etc.
So you're starting with the strongest.
So I'm starting with the strongest acid, yes. I'm actually putting this in terms that are even general to chapter 15 when we dealt with equilibrium constants, not even before Kas. You always deal with the largest equilibrium constant first. We'll just call it Kc. Always deal with the largest Kc value first.
What does that mean, deal with?
What does it mean, deal with? Create an ice table around. I'll put my literal quotes around that instead of my air quotes. Deal with means create an ice table around. Always deal with the largest Kc value first, then the next largest. then the next largest, then the next largest, etc., etc. And we did that without ever talking about it before. We dealt with an ice table around the strongest, the largest equilibrium constant. It was a Ka in this case. Then we did pH. That was the next strongest acid. And then, to be honest, we were out of acids that had any value to us. But you'll remember when we were talking about amphoteric bicarbonate, we will look at what the largest value of the equilibrium constant is for that, deal with that, and then deal with other things after that. Do you believe me?
Are you saying like largest compared to our constant of water? The
Largest just means largest. It just happened to be water this time.
okay.
And I will say this, water is always the last one that we do, because it is always going to be smaller than everything else. But what happened was, I always said, this always happens. Now we know this always happens last, because it's the smallest K equilibrium constant we care about. Do you believe me? Well, let me rephrase the question. Do you believe me that when we do this pH thing, we are really dealing with an ice table? Because we are. We could set up an ice table, we could have X, and we could have the concentrations, and we could show that everything, like, it's there. I don't think it helps to do it, but you are.
What would you do at the end with the concentration that you get? Would you add them together? I mean, if you did the second ice table, eventually you're going to end up with a concentration of hydronium.
Let's do it where it matters. Let's see. Let's do it with two acids, one strong, one weak. Then we will see what happens. So, because that's where we're going, is we're going to, you will be given a couple things in solution with their concentrations, and you will have to suss out for yourself which one to do first, based on looking at the conversion equation sheet to find out what its K value is, specifically for acids and bases. All right, so here's the problem. It says, what happens when two acids are mixed? What is the pH of a solution with 0.10 molar HCl and 0.10 molar formic acid? You don't have to know that name, but that's what it is. Formic acid, strong or weak acid? It's weak. It's got that COOH construction. Its Ka value, 1.8 times 10 to the minus 4 HCl, strong acid, right? I gave you its Ka value before. It was something times 10 to the plus 6. That is clearly larger. You will know that you already knew that it was a strong acid, and that whatever HCl we put in solution, 0.100 molar, what will be the concentration of hydronium from that? It's exactly the same concentration. Done from Chem 400. Anyway, let's see. Okay, so that was sort of no numbers, but all right. Always deal with the largest Kc value first. Ka for HCl. I think, was it 1.3?
Yeah.
I just have large on my page here, so. I'll put the plus in, plus 6. HCl first. Let's think about this for a minute. As far as ice tables go, where is the position of equilibrium for HCl? Towards reactants or products? Towards products, okay? Does this reaction go essentially 100%? Okay, so we're not even going to bother setting up an ice table, because the amount of reaction is all of it. But if you set up an ice table, it would go like this. 0.1 molar HCl minus 0.1 molar HCl with 0 left creates 0.1 molar hydronium and 0.1 molar chloride ion. So we don't need an ice table because the reaction goes to completion. And ice tables are for reactions that don't go to completion. Are we comfortable with that? Right? We did all of Chemistry 400 with nary an ice table because all the reactions that we cared about went to completion. So I'll make 0.100 molar hydronium and 0.100 molar fluorine. Questions about that? Okay, so formic acid next. Formic acid is a weak acid. We do need an ice table to figure out how much of that reacts. Oh yeah, it's going to get crowded down here. So I'll try and make my ice table a little smaller. Here's my ice table. It's got my Ka value at the end. We know that our initial concentration of formic acid is 0.100 molar. We know that we don't care about our H2O. We do have a non-zero concentration of hydronium. That's new. But it's additive. And so, Logan, I don't know if that starts to address your question, I think it was, about what do? You add it up and you keep going. And our mental process is, okay, all these reactions are going on at the same time. But mathematically, you can deal with the one with the largest K first as if it happened first. And then use the results for the next ice table and use the results from both of those for the next ice table. We treat them mathematically as if they occur in series. We still have none of that. We still have a 0 on the product side. We still have to go towards the products.
Would it be like
Question?
Would it be minus 0.1? Or I'm sorry,
Let's take a step back. We know we have 0.1 molar formic acid. That was in the problem statement. This 0.1 molar hydronium comes from the HCl. Here. I think I added an extra 0, but this is what we will do several times over, meaning, and this is what it means, always deal with, always take the largest K value here. Reaction goes to completion. Finish with it. Create your products. Then do the next equilibrium process.
So we're looking at it right now as two different reactions when really it's one. So we're breaking it up into two.
We're looking at it as if this reaction happens first, and then whatever comes out of it is the inputs to this one. Yeah. And that will always be okay. And the reason is, and this will always be true too, 10 to the plus 6, 10 to the minus 4, this reaction happens up 10 to the 10 times more. So you can deal with it first. And that's why we're establishing a precedent here, which is, this was 10 to the 9 actually. Deal with, and we were already doing it. So we're saying we're already doing it. Let's formalize more about why it's okay. And then do it again. But the reason is, this reaction occurred completely, and you can treat it as if this reaction happens next. Marissa?
I don't care. How did you get the 0.1 molar for the hydrogen?
Does it make sense how I got this number? HCl was 0.10 molar. HCl is a strong acid. HCl breaks up 100% into hydronium and chloride ions.
If you do an ice table, you're not going to get that number.
If I do an ice table for this, you're suggesting that I'm not going to get this number.
Yeah.
Would you like to see that ice table? So I'm going to use all this space. So where would you like it? I was going to put it down here. You can put it wherever you want. So ice table for HCl. Next page. The ice table I'm about to make for you is still a Ka ice table. That's still the equilibrium constant expression we're doing. It's going to be HCl plus water. Goes to hydronium plus chloride ion. Molarity ice. And we have an initial concentration. We don't care about water. We have approximately 0 hydronium. We have 0 chloride. Kate, question? Oh. Was that better?
Yes, I don't know the really makes a difference.
I don't know. I made up this problem with 2 sig figs. I tend to work in 3 sig figs, so I went back to default mode. All the numbers are the same. Does that work?
Yeah.
Yeah. That works. It's mathematically good. Okay. Where is this? That's the biggest exponent. I don't like. It's positive. It's the biggest exponent you'll see, figuratively and literally, for acids. Plus 6. What is the position of equilibrium towards products, right? We don't need x's in this table. We know how much reacts.
But if you didn't, and you did use reactions, why don't you?
Ah, okay. Hold on. So let me do this. For a second, do you see where the 0.10 hydronium comes from? Because I will do the next part next. Because the next question that Marissa's asking, it's a valid question. So why not put x's in there? We don't know. We know it's not 100%. We're assuming it's 100%. What if we wanted to figure out what exactly it was? You want me to do it? I'll do it. It's actually an interesting question, and we do get to it later. Okay? Actually, let me just describe the process now. And we'll do it later, I promise. Okay? So, if we wanted to do this ice table in terms of x's, what we would do is, well, we could put minus x here. But this reaction goes 99.9999%. So x is going to be 0.09999999. And XL will do it for you because it keeps all its sig figs. But for us, there's an easier way. And the easier way will be this. Take this reaction, assume it goes 100% to products. We know what the products are now. Then, flip your reactants and products. So now we have hydronium and chloride on the reactant side. If we flip reactants and products, what happens to our K value? it becomes its reciprocal. So instead of 10 to the plus 6, it's 10 to the minus 6. Can you do an ice table, or have you, or have I, keep it in terms of me, I have done many ice tables with 10 to the minus 6 with x's here. So the simplest way mathematically to actually find out how much less than 0.10 actually reacts is to assume it goes 100%, flip the reaction so that your K is 10 to the minus 6, and then do a second ice table to find what didn't react. And you would find that it was X was about 0.000. Anyway, I'm not going to do that now. That's enough time. Hopefully that leaves you with a little flavor for it. But that is what's called allow the reaction to go to completion, flip it, and then allow it to come a little bit back. And that will be a useful thing to do under some circumstances. But for now, all we need for this is this assumption that it goes 100% is a very good one. Because it's a strong acid. Yes. The difference between 100% and 99.9999% will not affect our results. Filling in our ice table here, now, I will point to this. This is new, right? We're not used to having a product here. And if this was 0, this reaction would go a little bit. If you put a number here, it goes that much less. So if you see a number right here, that means you can make the x is small approximation much more easily. Even though it's 1.8 times 10 to the minus 4. All right, here we go. I've written out the equilibrium constant expression. I will now write my equilibrium values on the top. And I will now, or I just did, write my Ka value. What I said is that we can assume that x is small. That means that x is smaller than 0.1 when it's subtracted from it. That means that x is smaller than 0.100 when it is added to it. And this is my favorite kind of math. Now I have x 0.1 over 0.1. These two terms cancel. I won't cross them out though. I will just say that x equals this number. Molarity. And you will find that that is less than 5% of our initial concentration. The assumption is good. Question?
I'm trying to like trace back why you assume both x's.
Good question. So why can you assume both x's are small? That's the question. Do you see, Anna, my small Ka value? It's tempting to do it. So it's tempting to do it no matter what the problem is. What I'm saying is, if Ka is relatively small, let's see.
So the last problem, it would have been significant because it was x times x on the numerator, and then it was like 0 something minus x on the denominator, so we were able to assume x was less than
I got it.
Okay.
Let's compare QC versus KC. Because QC always tells us which way we got to go. And we didn't say this, but if QC is very close to KC, no, that's not going to help us. Well, I was going to say, if QC is very close, it will tell you that we don't have very far to get to equilibrium. But QC is still going to be 0. So it still doesn't give us any new information. I tell you, so let's keep thinking about it. I don't have a good answer for you. Other than, if you are comfortable ignoring x here, it's still, like, whether it's added or subtracted, it's still an insignificant amount. What's new is we're ignoring it when it's added to 0.1. But the short answer is it's the same thing.
So say I'm on the exam and I ignore the x, and that's wrong too. I would get some weird answer. I could just check it and make sure, and then I would know not to ignore the x.
Right, and so if you ignore x and you get x equals 10% or 6% of our initial concentration, you know you can't anymore. That's still true.
Okay.
Okay. We're interested, what were we interested in? The pH. There we go. Our pH is actually, well, our concentration of hydronium is 0.100 plus x, so let's include that now. It's 0.100 plus x, which is 1.8 times 10 to the minus 4th. Which to 3 sig figs is still 0.100. pH is still 1.00. Conclusion, the HCl does all the significant acid here. Also conclusion, and I don't know if this is a conclusion, but in practice, treating the strongest acid, treating the largest Ka first, and treating subsequent ones later always works. Anyway, I think we're out of time there. Any questions? We'll take them after class.